So we've covered a lot in this chapter. It's one of the longest chapters, most challenging chapters, but we still need to talk a little bit. Isentropic processes. All that means is S2 is equal to S1. It's isentropic. Constant entropy, just like isothermal, temperature was constant. Isentropic, entropy, S is a constant during the process. We'll talk about isentropic efficiencies of turbine, nozzle, compressor, and the pump really are the same. They use a different term. If you're boosting the pressure of a compressible substance, call it a compressor. If you're boosting the pressure of an incompressible substance, call it a pump. And then we'll talk about the work for an internally reversible process. So for an isentropic process, if it was steam, if it was refrigerant, you just are using the tables, and maybe you know that S2 is equal to S1, open system, so it flows through the system. The inlet entropy S1, the exit entropy S2. If it's isentropic, S2 is equal to S1. Use the tables. For an ideal gas, though, we can do things with equations. We can analytically do a little more. So let's take a look at what it looks like. So we have for a delta S is equal to 0. What is delta S for an ideal gas? It's S. It depends if you're going to do variable specific heat or constant specific heats. Let's handle variable specific heats first. S2 naught minus S1 naught minus R natural log of P2 over P1. Does that equation look good? Does it look familiar? So this is for, let's say, air, and we're accounting for the temperature-dependent specific heats. You can also do this for gases like CO2, carbon monoxide. I think they have nitrogen. I think they have oxygen, but it's on a molar basis. So we have S bar naught minus S bar naught at state 2, state 1 minus R bar natural log of P2 over P1. There's a lot when we talk about ideal gases. We have a whole air table, and then we have tables for select other ideal gases, carbon dioxide, carbon monoxide. But that table is everything is on a per unit mole basis, not on a mass basis. So we have S bars and R bars, right? So that's equal to 0 for isentropic process. Okay, now come over here. Let's go ahead and rearrange this equation for air only. We have that S2 minus S1 is equal to R natural log of P2 over P1. Did I do the math okay? And then we can do this. We'll put the natural log of P2 over P1 equal to S2 naught minus S1 naught divided by R. That look good? Now we'll exponentiate both sides. So we have P2 over P1 is equal to, and when we exponent, remember this rule, e to the a minus b. Is that equal to e to the a? I'm going to ask two questions. Please don't shout it out. I want everybody to think. Divided by e to the b, or is it equal to e to the a minus e to the b? Is version A correct or version B correct? Both of these are in the exponent. E to the a minus b is equal to either e to the a over e to the b or e to the a minus e to the b. Have I given everybody sufficient time to think about it? And the answer is A. It's A. So let's employ that right here because of this minus sign right there. We'll get e to the s naught at state 2 divided by r divided by e to the s naught state 1 divided by r. Remember this, this was a function of temperature only. That's a function of temperature only. So what you've done is you've split it to a function of only temperature 2 divided by a function only at temperature 1. They give that function a special name. they call it PR, and you evaluate that PR at temperature 2, and this is PR at 1. What? What is this PR? It's a relative pressure. It's not the reduced pressure, it's a relative pressure. It really doesn't even have much of a name. It's in the tables, though, for the air table to help you do isentropic calculations with air. So this, let's take a look at where it's at in the air table and then how we would use it. Here is the air table A22 and out of our textbook. And we understand temperature column, enthalpy, internal energy. There's that S naught, right? There's that S naught. But we never really understood these two columns right here. And so they put a line and a line saying when delta S is equal to 0 with a little footnote. Go look at the footnote. We can look at the footnote in a minute. But what does delta S equal to 0 mean to you? Isentropic. Only for an isentropic process, use this piece of R. Okay? And it's a function of temperature only. So if I said I knew that the temperature was 250 Kelvin, then I can just get piece of R as a function of temperature. Okay? All right? And then let's say I somehow knew that I compressed it, and the final, this was, let's say, temperature initial, state 1. The final, state 2, gave me a piece of R of this. Well, then I can tell you what is T2. It's 290. All right? You almost have to solve a problem to see the utility of this relationship right here, that the ratio of the physical pressures for air that's an ideal gas that's undergoing an isentropic process, typically compression or isentropic expansion, is equal to the ratio of piece of R at T2 divided by piece of R at T1. Let's do this. I'm itching to see what that footnote was, so I'm going to scroll down in our table. It looks like piece of R and piece of R data for use with equations 641 and 642 respectively. That's the equation I just wrote. All right, equation 641 is this equation. Also, you can have also another one, that V sub 2 divided by V sub 1 is equal to V sub R2 divided by V sub R1. So both of these equations are for air accounting for variable specific heat undergoing isentropic process. How does that work? Let's say I come into a compressor and everything that the compressor takes in 100 kPa and it throws out, I don't know, 800 kPa. That's a bad looking 8, isn't it? 800 kPa air. And it says that that compressor is isentropic. Okay? How would I get it to be isentropic? It's well insulated, no heat transfer, hence no entropy transfer with the heat, and it's reversible, no entropy generation. One inlet, one outlet, no heat transfer, reversible, it's isentropic. Does that statement make sense to you? What are you doing? Oh, I'm sorry. Yeah, okay, he can't see the board, so he's doing it that way. It just catches my attention, like, what are you doing? All right. And so if it was isentropic, maybe you want to know T2, T2S, the isentropic exit temperature at state 2, knowing T1. Well, what you would do is you could say, I know the actual ratio of pressures. I know that P2 is 800. I know that P1 is 100, right? Maybe it came in at 300 Kelvin. Hence, I know PR1 at 300 Kelvin. I just go look it up. Right here, there's 300. Come over, grab the value. I know it's not pretty to grab 5 significant digits, but 1.3860. let's go back. 1.3860, and this allows me one equation and one unknown to calculate PR2. So PR2 is 8 times 1.3860. Anybody got a calculator? I have one. I should have ran this before I come into class, but so what we find is that PR at 2 is equal to 11.088, right? So this allows me to get T2S. What is the exit temperature? So let's go back to the table, and I'm looking for, that's the column of PRs. I come over here, here's PRs coming down, 11.08, looks like it's close enough to 11.1. I'm not going to do any interpolation. I'm going to tell you that that exit temperature is 540 Kelvin. See how you use it? Yes or no? All right, let's do this. Let's not do the variable specific heat. Let's do the same thing with constant specific heats. So if you used C sub P is equal to a constant, then what's my equation for S2 minus S1, which is 0? It's going to be C sub P natural log of T2 over T1, right? Minus R natural log of P2 over P1. All right. So we have to have a good value of specific heat, true? So let's go to our table. Let's go back here. Come on now. No, I don't want that. I want to get to the table for the specific heats for air. Here, okay, I can get it at room temperature about 1.005. But let's say I pick it at 1.01. All right, let's pick that value for specific heat of air because I know it's a little warm. So we'll pick, this value is 1.01. What's R? R bar divided by molar mass, 0.287. 8.314 divided by 28.97. Natural log, I don't know that exit temperature, but I do know that it came in at 300 Kelvin. And I do know that it went out at 800 kPa and came in at 100 kPa. So here's one equation with one unknown, and I can use this analytic equation to get T2S. Anybody want to run that for me while I run it myself? Let's see what that gives. Anybody get 542? What did we say without interpolation using variable specific heats? 540? See how we're doing it two different ways, but getting roughly the same answer? So that's that table, that's that column in the air tables. Okay, what happens if you want to do something for the isentropic process with CO2, CO, or other ideal gases? And if you want to use variable specific heats, you're going to just have to use and do it. You can still do it, it's just that this is a function of temperature only. So what you would do is you would get S2 bar naught equal to S1 bar naught plus R bar natural log of P2 over P1. You would look this up as a function of inlet temperature given pressure ratio, calculate it, and then get a value of S2 naught, and then go into the table and interpolate to get the exit temperature T2. Or just come down and use an equation like this where you're using a constant specific heat for that gas of interest. CO, CO2. There's almost too many methods. It confuses students, right? It's like too many choices. Deer in the headlights. Where do I go? I could go this way, this way, this way. Yeah, you could. All right. Isentropic efficiency. So we talk about the turbine, and we have it's a work producing or power producing device, true? And it comes in at state 1. If it's insulated, Q dot's equal to 0. If it's all internally reversible, what is sigma dot? 0. From the entropy balance, we find that the exit entropy at state 2 is equal to the inlet entropy 1. One inlet, one outlet operating at steady state. Typically, we are given temperature and pressure on the inlet, hence we look up S1. And down here, maybe we're given pressure on the exit. So these two properties allow us to look up, let's say, enthalpy exit, have the enthalpy on the inlet, and we can calculate the work per unit mass out of that turbine is H1 minus H2. I know we've done that. That's why I'm going a little fast. Hopefully that's music to your ears. Hopefully you're understanding. Yeah, that's right. That's what we're doing. You can even plot that on a diagram. Let's put it below. Temperature entropy diagram. There's the dome. Here's a line of constant high pressure. Here's a line of constant low pressure. You're out here somewhere. You expand it reversibly down, and you'll get the lowest temperature at the exit, the lowest enthalpy at the exit, the most workout. If you have irreversibilities, do a dashed line and go down to the same pressure but with higher entropy, and you'll get less workout. I did that right? Remember that? So now we have an opportunity to compare the actual performance to the best performance, the isentropic performance, using an isentropic efficiency. So we would say for our turbine, the isentropic efficiency of the turbine is the best that we can do, W dot over M dot, the best, assuming isentropic expansion between the two pressures, and the actual workout. So there's our isentropic efficiency, which comes out to be H1 minus H2 actual divided by H1 minus H2 isentropic expansion. Put a 2s saying I'm going from state 1 to state 2s. And a lot of times I'll call these other ones 2 actual or just say state 2. And so there is your definition of isentropic efficiency for a turbine. A lot of times you'll be given information and then you'll calculate the efficiency. Sometimes you'll be given the efficiency and then you have to calculate the performance. That you change problems around. How about for a nozzle? Well, what's the purpose of a nozzle? A nozzle is that you come in with flow here, you exit with flow there. The purpose is to have a high exit speed. Speed squared, take a half of that, a high kinetic energy. All right? So if the nozzle is insulated, so Q dot's equal to 0, which is easy to do, an insulated nozzle, and it's internally reversible, such that sigma dot's equal to 0, then the highest speed and the highest kinetic energy will be when it's isentropic. It's isentropic flow, such that V2S will be greater than V2 actual, or the kinetic energy at 2S will be greater than the kinetic energy at 2 actual. So here we have an efficiency for a nozzle, and the efficiency for the nozzle is what is your kinetic energy on the exit compared to the specific kinetic energy on the exit if it was isentropic. Let's go back to our first law. First law is very simple for this problem. If Q dot's equal to 0, sigma dot's equal to 0, just S2 is equal to S1. How about the second law? The second law, there's no shaft work, no heat. You find that I'm running out of room. I don't know how to be as efficient, but let me write it this way. H2 minus H1 plus KE2 minus KE1 If it is truly isentropic, that's a KE2S, such that KE2S is equal to KE1 plus H1 minus H2. So you use the first law to get the isentropic exit kinetic energy, and then maybe they give you this, or you have to calculate it knowing the actual exit kinetic energy. But this is the equation for the nozzle isentropic efficiency. All right, what about a compressor or a pump? Same discussion. That's why I'm trying to put it all on one page. If it's insulated, Q dot's equal to 0. If it's also internally reversible and insulated, the sigma dot's equal to 0, then it's delta S is equal to 0. It's isentropic. That's going to be the best performance of your compressor, best performance of your pump. Okay, you come in at state 1, you go out at state 2. The work of the per unit mass, and a lot of times you turn it around and you put it into the pump. Okay, let's show it going into the pump. That's going to be H2 minus H1. If it's isentropic, you'll get H2S minus H1. The efficiency of the pump, isentropic efficiency, will be the ratio of the smaller work to the greater work. Okay, what is smaller? Is this a smaller amount that work to boost the pressure? You're comparing the same pressures, right? So you're not going to compare a pump and say, okay, this pump is going to boost it from P1 to P2. I'm going to compare it with a different pump that has the same P1 but a different P2. No, you have to compare the same delta P for your pump. Just like for the turbine, you always brought state 2 down to P2, the same P2. All right. Let's go ahead and show it on a TS diagram, on a temperature entropy diagram. If you want to show it for gases, or if you want to show it for liquid, either one. Last time I showed it for ideal gas. Let's show it for a liquid, where you have a low pressure, P1, and a high pressure, P2, and pumps like, I'm sorry, not there. Pumps like either saturated liquid or compressed liquid. Okay, so it's going to boost it up, straight up right there. Doesn't look that exciting, does it? Well, so you're going to have the minimum work, W dot over M dot, minimum divided by W dot over M dot actual. And that'll be the isentropic efficiency of our pump. I pause, I ask, are there any questions that you might have? Have you been solving problems requiring you to use the isentropic efficiencies of pumps or compressors, turbines, as well as nozzles? Hopefully you have, right? Please do so.
Sorry, why is the isentropic efficiency?
Yeah, that always will confuse students. Just think of this. Should that efficiency be greater than 100% or less? I know the COP, coefficient of performance, we let to be greater than 100%, like factor 2 or 3 for the COP. But here, you want efficiency, the isentropic efficiency, to be less than 100%. And 100% be the best. So if it's 70% or 60%, you know, you're further away from 100%. So you want to put the larger in the bottom of the denominator, and in the numerator the smaller. And it's the smaller amount of work, which is the isentropic work, the least work in the numerator. That's the best I can do to explain it. All right? All right. air enters a turbine operating at steady state at 6 bar and 1000 Kelvin and expands isentropically to 700 Kelvin. Determine the pressure at the exit and the work per kilogram of air. So this is a turbine problem. So you could just show it as a black box. You can give it some shape, like we try to distinguish a pump from a compressor from a turbine, sometimes by the shape. But here we go, inlet state 1. It's all air, so ideal gas. It comes in at 6 bar and 1100 Kelvin, and it goes out at state 2, and it produces some power. And at state 2, it expands isentropically to a temperature of 700 Kelvin. What is the pressure? P2. That's what we're asked to find. And then what is the work per kilogram of air? We're asked to find W dot over M dot. That's what we're asked to find. Okay? Make sense? Well, let's see some of the key words. It expands isentropically is definitely a key word. Okay? So they've already used the second law to conclude that S, or that just by this definition, that S2 is equal to S1, or S2 minus S1 is equal to 0. Okay. We go and we write down for air accounting for variable specific heats, because it's such a high temperature, where we could use constant specific heats, but let's make sure and evaluate the constant specific heats at a high temperature in the range. Maybe evaluated at 900 Kelvin. If you wanted to use constant specific heats, evaluate the C sub P at an average temperature, and in this case it's around 900 Kelvin. It'll work. Either one will work. Okay. Let's vote. Constant specific heats or variable? Okay, all the hands for constant, raise. All the hands for variable, raise. It's split 50-50. Who wants to be the tiebreaker? I guess I'll have to be the tiebreaker, huh? What? Do them both?
No. I didn't vote.
Oh, you didn't vote? Yeah, you don't want to stick your neck out. Some people will throw eggs at you. Okay. It doesn't matter. Which one do we want to do? Do them both. We can do them both. So this is equal to the S2 naught minus S1 naught minus R natural log of P2 over P1, right? Go and look up S2 naught. That's at 700 Kelvin. Go and look up S1 naught. That's at 1100 Kelvin. You already were given P1. R is R bar over molar mass, 0.287 kilojoules kilogram Kelvin, right? Kilojoules per kilogram Kelvin for air. Guess what the only unknown in this whole equation is? P2. Solve for it. Okay? Somebody else says, why don't I do this? Why isn't P2 equal to P divided by P1 equal to PR2 divided by PR1? You just showed us that great column in air tables. Yes, you're exactly right. That'll work too. Look up this one at 700 Kelvin. Look up this one at 1100 Kelvin. Okay. Then take that ratio and then just bring that P1 over right here. Put the P1, bring that over. And solve for P2 that way. They seem like they're different, but they are the same approach. Did that make sense? Now let's do a constant specific heats. We have S2 minus S1 is equal to 0 is equal to C sub P, natural log of T2 over T1, minus R natural log of P2 over P1, right? So here, if you allow me, I'll just say known, known, can get from the table, but make sure and look up if you want a very good answer. Look it up at 900 Kelvin for that C sub P. That's a bad looking P, isn't it? There's a better looking P right there. And we know P1, guess what you do? You get P2. One equation, one unknown. All right, there's another way of solving this problem, because some people have taken this equation and they've manipulated a little bit. What they've done is they've put, I've done this algebra last time. Let me quickly do that again. We have the natural log of T2 over T1 equal to R over C sub P natural log of P2 over P1. See the algebra to go from there to there? See that algebra? Yes or no? You got it? Enough people got that algebra in their mind? Can I bring, okay, then I recall R is C sub P minus C sub V. What? Is that really true for an ideal gas? Okay, let's quickly rederive that equation. All right, how did we derive that equation? Is H equal to U plus PV for an ideal gas as well as any other substance? All right. Is H a function of temperature only? U is a function of temperature only? PV, is that equal to RT for an ideal gas? PV is equal to RT for an ideal gas, right? If I take this equation now, if I differentiate it with respect to temperatures, it's still a truthful equation. And now what is dH dt? What is du dt? That's not a time, that's a temperature. And what is the derivative of RT with respect to T? R. So that's, I just rederived it. R is equal to C sub P minus C sub V for an ideal gas. Let me ask this question. Does this depend on it being a constant specific heat? Or is that true no matter what the temperature is? If I went up at 900 Kelvin and I evaluated C sub P at 900 Kelvin, and then I evaluated C sub V at 900 Kelvin, and I took the difference, is that equal to R, which is truly a constant? It's not temperature dependent. R is not temperature dependent. For sure, that's true. But will this work at elevated temperatures, or is this only good at cold air? True at all temperatures. True at all temperatures, okay? All right. All right. I think this is why people don't like thermodynamics. There's just so many pieces of the puzzle, and it helps if you can remember them, right? It helps if you can remember some of these little things. All right, let's get rid of this now. And now, so this I can replace R over C sub P by C sub P minus C sub V over C sub P, which is 1 minus 1 over K, which is K, oh boy, it's K minus 1 over K. There you go. So it's K minus 1 over K. Did I do the algebra okay? All right, so now what I want to finally do is take this up and put it over here before I take and exponentiate that equation. So when I exponentiate that equation where I have the natural log of T2 over T1 equal to exponentiate the natural log of P2 over P1 raised to the power K minus 1 over K, then I finally get that T2 over T1 is equal to P2 over P1 to the K minus 1 over K. This looks so radically different than every other thing that students get lost. True? Do you feel lost? Yeah, you're honest, that's right. You do feel lost. But sometimes they just look at the equation sheet, they say, I wonder if that equation will work. Well, I don't have much time. I hope it works because I'm using it. Right? To be accurate though, for this problem, you should evaluate K at what temperature? 700 Kelvin. Quickly, let's jump to the air tables. And here is 700 Kelvin, so I should use a value of 1.364 for K. And that equation will give me a very good answer compared to the temperature-dependent air tables. Well, I thought I was solving where the average temperature is 1,000 and 700. So I add them. Oh, it's at 900. You're right, 900. It's at 900 Kelvin. So, oops, getting close to the end of that table, aren't I? So use a K of 1.344. Thank you for that correction. Okay? All right. All right. That's too many ways to solve for the exit pressure. But once I have the exit pressure, what about the work per kilogram of air? Did you know I don't even need to do anything for part A? I can go right to part B and solve it without knowing the answer to part A. Because when I do the first law for that, let me just kind of write it in down here, that we have it's W dot over M dot is equal to H1 minus H2, and those H's are a function of temperature only, so that's 1100 Kelvin, and this one is 700 Kelvin. You just evaluate the H's. Or you could use C sub P T1 minus T2, could you not? And this C sub P you should evaluate at 900 Kelvin, the average temperature. True? Very good. Ready to press forward? Carbon dioxide, CO2, enters a nozzle. So we have a nozzle problem. And it operates at steady state. So it comes in at 28, pressure inlet 28 bar, and 540 Kelvin, temperature inlet. Inlet speed of 50 meters per second, and it exits at a pressure of 1.2 bar, temperature 2 of 340 Kelvin, and a V2 of 580 meters per second. Determine the heat transfer per kilogram of the CO2. Let's just do this step by step. Let's solve for A by itself. Why do I put a dash line like this? What am I doing? Saying that's my control volume, right? And it's a heat transfer. I'm going to assume that the heat transfer is in, Q dot in. And if I get a negative, it's opposite of in. True? All right. Is there any W dot out for this control volume? No, it's a nozzle. So I write the first law, and I find that Q dot coming in equal to the mass flow rate, and then we're going to have H2 minus H1. Should I stop right there? This is a nozzle. What do I need to include? Kinetic energy. Oh, you're good. You're good. Plus KE2 minus KE1. Now I stop, and I know that you can do that. Maybe it takes you 2 or 3 lines to get there, but does it look right? It doesn't? Oh, M dot. Now do you like it? So Q dot divided by M dot is the answer that I'm looking for. Heat transfer per kilogram of CO2. Make sense? All right. So I look up, I know that I have a table for carbon dioxide, but they give me H2 bar. How am I going to go from H2 bar, H1 bar to H2 without the bar. I'm going to use M. Either I'm going to multiply by M or divide by M. First of all, remind me, what is M? Molar mass. And for carbon dioxide, the molar mass is maybe 44.01 kilograms per kilomole. The numeric value, I have to look and remind myself, yeah, that's 44.01. Is it kilograms per kilomole or kilomoles per kilogram? Which way does it go? Kilograms per kilomole. You just have to memorize certain things in life, okay? If you were the first person to introduce molar mass, maybe you would have been more comfortable, have the inverse. But everybody in the world now, molar mass, kilograms per kilomole. So which way do I want to go? Divide by cap M? Yeah. Look good? And now, what about these kinetic energies? It's 1/2 the velocity at the exit squared minus the velocity at the inlet squared, right? Okay. So I just go to the table for the carbon dioxide and I look up at the exit temperature of 340 Kelvin. I look up, I think it's 10,959. And then I have it for 540 Kelvin. It's 19,485. Those have units of kilojoules per kilomole. And then I have 1 over 44.01 kilograms per kilomole. Okay, that finishes out the H's there. Plus 1/2, we have the velocity exit 580 squared minus the velocity inlet 50 squared. All units of meters squared per second squared. Use the unit conversion factor whenever you have to combine kinetic energies with enthalpies. That 1,000 meters squared per second squared is a kilojoule per kilogram. Don't forget that conversion factor. And I'm running out of room, but Q dot over M dot comes in at negative 26.8 kilojoules per kilogram. What does the negative sign indicate? It's really the nozzle's hot compared to the surroundings, and so there's heat transfer from the nozzle to the surroundings. What is the change in the entropy for part B of the CO2? Are they asking for S2 minus S1? Can I just get that as S2 bar minus S1 bar times 1 over the molar mass? Or 1 over the molar mass times S2 bar naught minus S1 bar naught minus R bar natural log of P2 over P1. All of those work, right? Yeah, they work. It's just that I had this only on a molar basis, but when I wanted to evaluate it, I have to get the temperature dependent only part and have the minus R bar natural log of P2 over P1. Okay, I go to the same table, the next column over at those temperatures and get these values, the molar mass we used, and you calculate a change in entropy. The change in entropy is 0.1497 kilojoules per kilogram Kelvin. So that's S2 minus S1. Does that look good for part B? I know I have 4 digits on that. That's excessive. I have to round it off. 1.50. 1.50. Yes. Oh, no, they're not on the table, so I have to do that. All I'm showing is the 1 over the molar mass. Maybe I should have left it like that. So I'm saying if I want it on a kilogram basis, I'll get the difference on a molar basis and then divide by molar mass. How do I get the difference on a molar basis? Use the S-bar knots out of the tables. Good. Now, what you have is a larger control volume such that this boundary temperature, TB, is 298 Kelvin. So when you do a large control volume, second law analysis, which I don't have enough room to write down, can I scroll down, or do you want me to just squeeze it in? Scroll down? Okay. So when we apply the second law, 0 is equal to Q dot divided by TB, that's in, Q dot in, the sign convention, plus the mass flow rate times S in minus S out plus sigma dot. All right? You like that second law? And so we're interested in the entropy production per unit mass flow of the carbon dioxide. So that's going to be equal to a minus Q dot divided by M dot divided by TB plus S2 minus S1. Just a little algebra right there, true? And so I'm glad we computed the Q dot divided by M dot using the sign convention. So that's negative of a negative 26.78 kilojoules per kilogram divided by my 298 Kelvin boundary temperature plus the change in entropy we just calculated, 0.1497. Glad I have it to 4 digits. Kilojoules per kilogram Kelvin. And now we calculate sigma dot over M dot to be equal to 0.240 kilojoules per kilogram Kelvin. You like that? You see how we did that? Yes, yeah. It's given in the, otherwise it's impossible. And it says basically do an enlarged control volume such that you get out to a constant boundary temperature. And that's 25 degrees C, so 298 Kelvin. Ready for the last part? Isentropic efficiency of this nozzle. Well, this is a little bit of a challenge. Let me try and tuck it in. I'm going to go up high. How's that? So you can still read the problem statement and look at this nozzle. The isentropic efficiency of a nozzle is some kinetic energy divided by some kinetic energy. Specific. Both of them are specific kinetic energies. It's the specific kinetic energy actual divided by isentropic. Isentropic, we know or can calculate the actual kinetic energy. It's 1/2 V exit squared. So the actual is 1/2 580 meters per second squared. I need to calculate the V2S and then square it. That's what I need to calculate the efficiency. Well, if I come back to this problem, I'm going to have to say that for isentropic efficiency, what do I conclude about entropy generation? I need to set that equal to 0. What do I conclude then if there's no entropy generation and I need delta S to be 0? I can't have any heat transfer either. So I know that my first case I have some heat transfer and I have some irreversibilities. But I'm going to compare and compute an isentropic efficiency for this nozzle assuming no irreversibilities and no heat transfer, hence isentropic expansion. So I go back and I say the inputs are fixed into this nozzle. The input of the pressure of 28 bar, the input of the temperature of 540 Kelvin, the input of the speed of 50 meters per second. And now I want to assume no irreversibilities, no heat transfer, hence it's isentropic expansion, and I want to calculate the exit speed V2S. Yes? Because it's an isentropic efficiency, and so I have to do that, no heat transfer. Well, you do this, you basically have that's equal to the square root of the inlet speed squared plus 2 times H1 minus H2 bar divided by the molar mass. All right? But I have to get the exit based on isentropic expansion, and not H2 as I previously had, but H2S. How do I calculate H2S? I go back to the equation 0 is equal to S2 bar naught minus S1 bar naught minus R bar natural log of P2 over P1. The pressures I know, universal gas constant I know, this temperature dependent component of the entropy at the inlet I know, hence I calculate S2 bar naught, and when I calculate that I find it comes in at 212.104. I go to the table, I interpolate to find H2S, H bar 2S, and when I interpolate it's 8904.5 kilojoules per kilomole Kelvin. Finally, I can stick that in and I calculate that the exit speed would be 695.2 meters per second if it had been truly isentropic expansion through the nozzle. But it only came out at 580 meters per second. See how that's better, faster if it's isentropic? Hence, I can calculate 695.2 squared. The efficiency of the nozzle is equal to around 70%. So somebody asked, and so I included the interpolation right here that was needed to get, when you get S bar naught to be 212, then you want that H bar as well as the temperature. I just interpolated the temperature just for completeness. All right. But that's the value that we use for this H2S right there. Okay. Ready to move on? Okay. Oh, this was showing you how to go through the tables using this S bar naught and carbon dioxide table. All right. Now we move into a section. It's the very last section of this chapter. It's entitled Heat Transfer and Work for Internally Reversible Steady Flow Processes. So think of an open system, which is a control volume, and we have a single inlet M dot going with a single outlet M dot. So it's just M dot flowing through the system. You can have some power, W dot, being developed. We'll stay with that sign convention. And the sign convention is Q dot in. We have state 1 on the inlet and state 2 on the exit. We could talk about the typical enthalpy, entropy on those inlet and exits. Let's write the first law. First law, and the second law. Second law. for this system. What does the, let's start with the second law actually. Let's write the second law. If it's steady state, 0 is equal to 1 heat transfer coming in at some boundary temperature. We'll have the mass flow rate bringing with it entropy, taking out entropy, and entropy generation. Do you like it? Now, it said it was internally reversible, so that's also equal to 0. So steady state made that equal to 0, and that's why I didn't even write that term. But here you go. So here's a reduced form. Can I rewrite this equation as Q dot divided by M dot? Haven't we done that before? What is the heat transfer per unit mass flow? Equal to TB, but I have to switch S2 minus S1 because I brought that Q dot to the other side. So there's some algebra. Did you follow it? Look good? And if the temperature of the fluid varies as you're going through here, and yet you're transferring heat in or out of the fluid as it's varying as you transfer in and out, you can replace on the left-hand side, well, you can the net by an integral of the fluid temperature as it's transferring through, the boundary temperature changing, ds, from 1 to 2. If the temperature was constant, you would get a TB, but here you can see that this right-hand side can be replaced by integral of TDS. Hence, the notion that on a temperature entropy diagram, if you have a process 1 to 2, so it's flowing in at state 1, flowing out at state 2, its properties are changing along the route, and you know how they change along that route inside the system, then you can do an integral of the area under the curve, and that's a physical representation of the heat transfer per unit mass. Integral T on the TDS diagram, integral TDS. But this is only for solid lines, internally reversible processes, okay? Q dot over M dot int rev. Is that true? That's a review. I think we already had that. But now we're going to go and do it for the first law. Let's write down the first law. W dot out of the control volume per M dot equal to Q dot into the control volume per M dot plus H in minus H out plus kinetic energy in minus kinetic energy out plus potential energy in minus potential energy out. I know there's a couple steps there, but can you get to that equation in your own mind? Does that look good? All right. Well, we can, if it's internally reversible, because that's what this section is covering, the heat transfer for an internally reversible open system, steady state flow through the system. Now we're dealing with the work transfer for an open system where there's steady flow through the system and it's internally reversible. Okay, so this one we can replace by the integral T ds from 1 to 2. True? All right. This is a couple different ways of doing that, but it's, can I put, here I'll put an intermediate step, minus H2 minus H1 plus, I'll leave the rest of the kinetic potential energy there. So could I write that this is equal to minus the integral of dH from 1 to 2 with the kinetic energy and potential energy there. You see? So I can put these together that you have the integral from 1 to 2 TdS minus dH. If that makes sense. All right. Or what is a relationship between, or just leave them separate, just leave them like that. What is a relationship that we recall, one of our, property relations in chapter 6? It was one of the TdS equations. TdS is equal to dH minus VdP. True? So if I integrate, so the integral of TdS minus the integral dH is equal to the minus the integral VdP. So I replace both of those by an integral from 1 to 2 of minus the VdP. And then I still have the kinetic energy in minus kinetic energy out. And I still have the potential energy in minus potential energy out. But this is W dot over M dot. It's also because we replaced, it has to be for internally reversible, because we used that assumption right here on Q dot. Often, but not always, those changes in kinetic energy and changes in potential energy are often 0. So we're left with this funny equation. The first time you see it, you say, what? But here it is. It's equal to minus the integral from 1 to 2 of V dP. What? Well, if the specific volume is a constant, this can come outside the integral, and the work is the minus V P2 minus P1. Now, when do we have that? We have a case, this often applies to a pump. A pump. So you have a liquid coming in, liquid going out. The purpose of the pump is not to change the volume of the fluid flowing through it. The purpose of the pump is to boost the pressure from P1 to P2. The pressure goes up. So if I check the specific volume of the fluid coming in, V1, and I compared it to the specific volume of the fluid going out at V2, they would be essentially the same if it's a liquid. And we have a lot of liquid pumps in practice. So the specific volume of the liquid doesn't go up or down, it stays the same, but the pressure went up or down. So this tells me the minimum work per unit mass that is required to boost the pressure of that fluid. Does that make sense? It's just the integral, or it's just VdP. Now, this minus sign, what does that say? Well, it's negative work out for a pump if the pressure outlet is high. Okay, so this works for a liquid water pump or another pump that handles liquids. Does it work for a hydraulic turbine? What's a hydraulic turbine? I mean, I know steam turbines, but what's a hydraulic turbine? It's like on a big hydroelectric generating station. You have a big dam. You have a lot of liquid water backed up. It's a big lake behind you, right? That you put it through a specific turbine. The turbine doesn't change the volume of the liquid flowing through it. It just drops the pressure. As it drops the pressure, it extracts a lot of energy out. You can use the same thing here. Here, the same equation works. This would give you not just the minimum, in this case, because it's a work extracting, the hydraulic turbine, it gives you the maximum power or the maximum work out, same equation, minus V P2 minus P1, but the exit pressure is lower than the inlet pressure for a hydraulic turbine. So you get a positive power out, or a positive work per unit mass out. All right? A lot of times students look at and they say, look, I learned work is equal to F dx. I multiply by area, I divide by area. That's equal to pressure, force per unit area, times a change in volume, PdV. I understand work is equal to PdV. Now you're telling me work looks like V dP. What? It looks backwards, doesn't it? This was for a closed system. This is for an open system, a flow through the thing, okay? And there was a lot of steps involved with it, but this is for the reversible work, the internally reversible work, okay? I could put a cap V here, but when I divide by the m dot, then it becomes a specific volume. Just like over here, if I divide it by the mass, then it's P dV, something like that. Okay? All right. Okay. We have a water pump. It receives liquid water at 50 degrees C and a mass flow rate of 20 kilograms per second, and it exits at that pressure 1,000 kilopascal. Determine the minimum power required to drive or run the pump. Whenever you see this word minimum, you're thinking second law, right? Second law. You're thinking internally reversible. True? So what you have is the pump comes in at 50 degrees C and it's saturated liquid, and it goes out at 1,000 kPa, and the mass flow rate m dot is equal to 20 kilograms per second. Well, the minimum power out, W dot divided by m dot, minimum will be, assuming it's internally reversible, and we just showed that it's equal to VdP, delta P. Okay. I'm gonna, if a lot of times we get tired of those negative signs, so we just say, look, this is work going into the pump. I know it's into the pump, so I'm going to calculate and report a positive work. So what is the specific volume? Well, first of all, what's the pressure that it comes in at? How do I find that pressure? It's the saturation pressure at 50 degrees C because it's saturated liquid, 12.35 kilopascal. All right, so there it is. How about the specific volume of the fluid, V? Well, I know what it is at 1, it's saturated liquid, so I'll calculate that 0.001021 meters cubed per kilogram. So the answer is 0.0010121 meters cubed per kilogram for the specific volume. The change in pressure, 1,000 minus 12.35 kilopascal. I recall the unit conversion that a meter cubed times a kilopascal is a kilojoule. True? And we find that W dot per M dot, the minimum, is right at, well, also I wanted to calculate the minimum power, sorry. The minimum power, W dot minimum, is equal to M dot times all of that. So it's 20 kilograms per second, and when you compute it's right at 20 kilowatts. $20 kilowatts. if the pump isentropic efficiency is 72%, determine the power required to run the pump. Well, we calculated the minimum power required, but what's the actual power required if the isentropic efficiency is 72%? This is all balled up, sorry. That's W dot minimum. Is W dot minimum divided by the efficiency of the pump? Is that equal to W dot actual? It is. And so you calculate that 27.8 kilowatts are required to drive the pump. Does that look okay? All right. Move on a little bit. Now, here's a question. There's two of them. Saturated water vapor at 100 kilopascal enters a compressor and exits at 3,000 kilopascal. Let's just jump down here. Saturated liquid instead of saturated water vapor enters at 100 kPa and it now enters a pump, but the same pressure and the same pressure. See that? So a compressor to boost it from 100 to 3,000 or a pump to boost it from 100 to 3,000. But what does the compressor ingest? Saturated vapor. What does the pump ingest? Saturated liquid. All right. It is compressed isentropically, the same sentence for both of them. Determine the work required to pump the water. Compress the liquid or water and describe the state of the water exiting the compressor. So part B is probably easier to answer for both of these first. Describe the state of the water leaving the pump. How about I stop and you answer part B for the first and the second question, okay? Write it down. All right, some of you got the first one right away, and that is what comes out of the compressor. Anybody that got it correct, I may have said, oh yeah, you got the first one correct. How can you describe what went on in your mind that you got it correct? Only those that I know, I said, oh yeah, you have it correct. What went on in your mind? How did you determine it? TS diagram. See, I'd rather some student say, let's look at the TS diagram, than me say to you, look at the TS diagram. But if that's a hint, see, look at the TS diagram. So if you plotted the TS diagram, temperature entropy diagram, you'd put on there the dome, and you would say, I'm at a low pressure. Let's put a line of low pressure like this, and the line of high pressure like this. True? And this pressure is 3,000 kPa. This pressure is 100 kPa, right? Okay. So the first case, the compressor, what does it take in? Saturated vapor at 100 kPa. Where is it at on this TS diagram? I'm going to pause and make sure you can get that. You put the inlet to the compressor on this TS diagram, and you put the inlet to the pump on this TS diagram. And if you do that, I think you got it down. You got this problem nailed. All right, so a lot of people now, they say, oh, this is an easier problem than I thought, right? So this is the inlet to the compressor, saturated vapor at 300 kPa. This is the inlet to the pump, saturated liquid, saturated vapor, saturated liquid at 300 kPa, right? The pump boosts it up to 3,000, just like the compressor does. The compressor goes, if it's isentropic, the best that it can do is right there. There's 2 and state 1 for the compressor. Here is 2 and 1 for the pump. Now, I've grossly exaggerated, but I walked around the room and I saw some of your TS diagrams. They're worse than mine. You've really grossly exaggerated. But you know that temperature of 2 at the outlet of the water pump is only going to be insignificantly greater than the temperature at 1. Those lines are very close together. It's very hard to draw it like that. That's why we exaggerated them and separated them out. But it's not like this temperature is way up there compared to that lower temperature for the pump. The pump outlet is pretty cool. All right? Does that make sense? So now that you're armed with that, we can now look at the part A question. What is the work required to compress the water? And so the work per unit mass, or W dot per M dot, to compress the water for the compressor, right? And this would be the minimum. It's isentropic. So it's internally reversible. It's going to be H2S minus H1. True? First law, where you've embedded it to get the H2. It's S is constant. And then W dot M dot for the pump, you can do the same thing. It's H2S minus H1, but we know that in both of these cases it's the integral of V dP, the integral V dP. But guess what? This V can come outside, but this one cannot come outside. All right, for the pump, why can the specific volume come outside that integral? This liquid is staying constant. And why can it not come outside the integral on a compressor? It's significantly being compressed. The specific volume on the outlet's much different than the inlet. Okay, if I plotted a pressure volume diagram, and I said, here's my dome, blah, blah, blah. And right here is, I'm going to boost the pressure from this pressure up to, what did I say, 3,000 pressure. It would look like this through the pump. V stayed the same, and it's just that. You know that it's kind of funny, but the integral of VDP on a PV diagram is the area to the left of the curve. All right, let's try and do it out here. It goes like this. And if I knew the path, I could do the integral and the area to the left of that curve. That would be fine, but I don't know the path. I don't, okay? Now, a vicious instructor in thermodynamics may make up a curve and give you some polynomial expression for that P as a function of V, and then ask you to integrate on these kind of weird axes because you're doing the area to the left, right? It's not under the curve. It takes students a while to figure that out. But when you do the math on this one, what you find is that for the compressor, it takes a lot of energy. It takes 881 kilojoules per kilogram. For every kilogram of water, I have to put in 881 kilojoules of energy to boost its pressure from 100 to 3,000. That's the minimum work. That's everything's perfect, a perfect compressor. Now, what about for the pump? 3.03 kilojoules per kilogram. Let me ask you this. You owe me some money. I forgot. Is it $3 or $881? I can't remember. You know, which one would you rather pay me if you owed me money? I mean, these numbers, sometimes we lose track of their meaning. But there's a big difference between $3 gasoline and $881 per gallon gas. What do you want to buy? Huh? This is a huge difference. This is a huge difference, right? It's a big difference. This is one of these little observations I hope you come out of this class with. It takes a lot less energy. Even with the best machine, we're comparing the best compressor and the best pump. Head to head. Let's do a comparison. If I want to do 1 kilogram of water from this pressure to that pressure, it's a lot easier to do it in the pump when it's saturated liquid. Okay. What does it come out of the pump as? Set compressed liquid. What does it come out the compressor as? Superheated vapor. Okay. Does that make sense? Who's ever heard of Bernoulli? Who's ever heard of the Bernoulli equation? Who can write from memory Bernoulli's equation? Does anybody remember how you used it in physics? Something about head. I heard somebody say head. Airflow. What else did you remember? Head, airflow. Any other words? Bernoulli's equation. Fluid mechanics. Flow along a streamline, steady state. So what they said was, oh, here's this fluid chunk and he's flowing this way and that way, and then he's finally over here. And he's changed elevation, right? And he's changed pressure, and he's changed speed. But another millisecond later, there's another fluid chunk taking the same path because it's steady state, and that fluid chunk is going to end up doing the same thing, going from state 1 to state 2, changing elevation, changing pressure, changing speed. Does this remind you of Bernoulli's equation? Something that said that the pressure at any point plus 1/2 rho v squared at any point plus rho gz at any point along that path, let's say at point 1, compare it to the pressure plus 1/2 rho v squared plus rho gz at the end point or any point. It's a constant. It's always a constant along the streamline. There's a couple assumptions in there. The fluid isn't being heated up so it expands. There's no viscous dissipation of mechanical energy. Okay? But P plus 1/2 rho v squared plus GZ is equal to a constant. We apply that for inlet to outlet along a streamline in a lot of applications. So Bernoulli's equation we can now derive here. Let's go back to that equation where we had the work, the power, m dot int rev, and we had the minus the integral VdP, and then I'm going to put minus the change in kinetic energy, or do it this way, 1/2 V exit squared minus 1/2 V inlet squared minus GZ exit minus GZ inlet. All right. Now, if there is no power coming into my control volume, I put a long control volume like this. All right. If there's no power, that's equal to 0. No mechanical energy in or out. Then I say it's incompressible. V comes out. What I get is V P2 minus P1. Don't forget that minus sign. Minus, I could have written this KE2 minus KE1. Minus PE2 minus PE1. All right, let's get rid of this minus sign, this minus sign, this minus sign. They're all pluses. It's all are equal to a constant. That constant is 0. And what it says is that, what is the specific volume? Is that 1 over density? So this is replaced by 1 over the density. So I'll put the density up over here and over here, get rid of it there. And so I have P2 minus P1 plus 1/2 rho V2 squared minus 1/2 rho V1 squared plus rho GZ2 minus rho GZ1, not a subscript, Z1 is equal to 0, or P2 plus 1/2 rho V2 squared plus rho GZ1 is equal to P1 plus 1/2 rho V1 squared plus rho GZ1. I'm trying to rewrite this, but it's Bernoulli's equation. Bernoulli's equation was that equation. It didn't look like it. It didn't look like it, did it? You say, this is thermo. It's completely separate from any other class and any other topic. I've never learned anything like this before. But no, no, no. Here's Bernoulli's equation right at the end of chapter 6. Nice. You just have to put a control volume. You just have to put a control volume along that streamline in which that fluid pack is flowing, and there's no heat transfer. There's no work. It's all a balance of mechanical energy. The three forms of mechanical energy: your flow energy with the PV, your kinetic energy, and your potential energy. All right. I think we're done for today. Thank you very much.